Okay. Let me introduce myself. My name is Daniela, and I'm going to be I will be guiding the practice time in this camp. First, please, I'm going to share in the Zoom chat some links that are going to be useful. In the first drive, we have the PDFs that I'm going to use during practice, and the practice code and data is going to be in the GitHub link, and the Google Colab link, which is the tool we're going to use, is provided in the last link. So first, please go to the GitHub link and download the code using this zip. All the materials for the camp will be here. And the folder is called Tutorials Master. Now let's start a little bit with a brief introduction on why it is convenient to study PyTorch. Of course, this is not the only library that is meant for deep learning or machine learning in general. There are other libraries like TensorFlow, which is also very popular. I'm sure you heard about it. But if we look at the trends of some of the top international machine learning conferences, the use of PyTorch in the submitted papers is surpassing their TensorFlow counterparts. So these are a bunch of the most important international conferences of deep learning. And as you can see in time, we have more submissions that use PyTorch code than TensorFlow. Then what's the benefit of following this trend? Think about this. If more people use this library, then more people can suggest updates or fix bugs, or then the library and the creators are going to be active in renewing and making this tool better. So this is a good reason to learn PyTorch. You can visit the PyTorch homepage and install the library according to your preferences in your own desktops. But for this camp, you don't need to do this because we're going to use a platform provided by Google called Google Colab. So in the link I shared in the Zoom chat, you can go access to Colab, and this window will pop out, and we're going to go ahead and open a new notebook. So we're assuming that you are already familiar with Python programming language. Colab is really straightforward to understand and use. We're going to start by clicking this block. This block is called cell, so we can just start by writing down our typical phrase. So, hello world. Please, if you can follow at the same time I'm doing this, that would be really good of you. To run a cell, we just can press this play button, and after a while, it's going to print our code. To add another cell, we can just put our cursor here and click code or add code manually by doing this. Okay, so now we're going to dive into what PyTorch is. PyTorch is a Python-based scientific package that is meant for two types of users. First, for NumPy users who want to use GPU. GPU is a parallel computing tool. Parallel computing is really a really good tool to use for this type of computation burdens when we train neural networks and etc. Because it's like having several workers. It's like having several students computing the same thing at the same time. So we save a lot of time and a lot of resource. And also, this library is optimized and made efficient for maximum flexibility and speed for deep learning purposes. PyTorch uses tensors. Tensors are generic n-dimensional arrays for numeric computation. So it's just an array that we can use to compute different things. So let's go ahead and try. Let's first import our library, import torch. And we're going to create some random tensors. So I'm going to define a tensor X of dimension 5, 3. And then another tensor called Y, also of dimension 5, 3. You can experiment with whatever. And we're going to print both tensors. And this will print some random tensors that can also have not unknown values, or you see they're completely random. Okay, let's move on. We can also convert torch tensors into another type of array, for example, NumPy arrays, and vice versa. So we can go from one to another. First, we're going to create a torch tensor consisting of just ones. For example, we want torch tensor with 5 ones. See what that gives. And we're going to convert this tensor A to a NumPy array by calling this function. So let's also see what that gives. And we're going to go from this B. Now B is an array. So let's convert this array into a tensor again. So as you can see, we went from having a tensor A and then having a tensor, an array B, and then going back to having a tensor. So as I said, one of the benefits of PyTorch is the ability of use GPUs. To use GPUs, there is one platform called CUDA, which was developed by NVIDIA, that allows us to send any of these tensors into a GPU computing environment. So first, what we're going to do is we can turn in Colab this GPU for computing. So if you go to edit notebook settings, we can choose manually our hardware acceleration. In this case, we want GPU. So go ahead and change it. And to check whether the GPU is active or not, we can type torch CUDA is available. You see now GPU is active. Okay, so now what we're going to learn is how to send these tensors to this CUDA device, in this case to GPU. So we have the tensor. You can define a tensor of ones. And now what we're going to do is to send this tensor to a CUDA device. One of our options is to send it by .CUDA. Another option is to send it with the function to torch device. So run that, and now let's see if this will take some time. So as you can see, A is our normal 5-1 generated tensor. Now let's see B after we send A to device. As you can see, now it's a tensor, but now it's placed in our device. And C we was doing the same with another kind of notation. So again, we're having a tensor A sent to the device. PyTorch comes with a convenient automatic differentiation engine called AutoGrad. As Professor said, we don't need to calculate all the derivatives for back propagation by ourselves. And PyTorch has this automatic engine that is really convenient. and really easy. We just need to call one line that I'm going to explore more in the practice. One of the main things that PyTorch lacks is visualization. As Professor said, visualizations is really important to track our experiments. It's also part of the analysis. So we can use always matplotlib, which is the default library generally used for computing that Python offers. The problem is that we need to finish our experiments usually for a visualization. We cannot have a real-time follow-up of our experiments. Other options that PyTorch offers is TensorBoard, which is from the library TensorFlow. Or there are other tools that you can work with. For example, there is this online tracking software called Neptune AI. And Neptune AI offers some experiments tracking, and that is really convenient to organize your experiments and follow them in real time. So while we are printing, for example, our training loss, we can see epoch by epoch how it's coming out, and we can know immediately if we have any issue. Also, we can conveniently store everything automatically with our results, and we can compare between experiments. For example, these are two experiments I run with different parameters in different days, and I can compare the test negative log likelihood of them automatically. So this is really convenient tool. So if you can explore it later, that would be great for whatever you need these experiments for. It's really easy to implement to your own code. So feel free to explore. We're going to continue. So there is the most important module for deep learning is TorchNN from neural network module. This provides a predefined efficient network definition. So we can use these built-in modules to use any network we want. For example, the feed-forward network that Professor explained, CNN for images, RNN, or any other type. There are more. Thanks to this, we don't have to program them from scratch. So this is really convenient tool. And also because of this, they may contain some internal attributes that are beneficial for analysis. So for example, when we have a convolutional layer, we have an attribute called self-weight, where we can store all the weights of our neural network. Also, this module provides some activations. Every activation, I think it has almost every activation known until this day. So this is what a general definition of our network looks like, and I'm going to go into detail with some examples. So this is a feed-forward network, as Professor explained. This is inspired by biological neurons. How do we go from this figure into our structure for our model in PyTorch? We initialize our network layers in this init method, and we're going to use the predefined hidden layers from the library TorchNN. So we're going to call, you see, 1, 2, 3, 4. We have 4 linear layers, and in each linear layer, we're going to define the dimension of the input that the layer is going to receive and how many neurons we want. So the next feed-forward linear layer is going to contain the input, which is going to be the output of the previous linear layer, and how many neurons is going to have, and so on. So for example, if we are thinking about image classification, we have an input vector X, which represents one picture that is going to be composed of 784 values. It's a flattened image. As Professor explained, we need a vector, one-dimensional vector. And this is going to go through each one of the layers. And then we're going to obtain the probability. So for example, we want to classify between 10 classes. We have an image of a number between 0 and 9, and we want to know what image is this. from. So we have 10 labels, and we're going to output the probability of this picture being one of these numbers. And the network is going to give us which label is the one that this image represents. How do we do that? So this module subclass is going to implement all the operations on the input data in the forward method. So we have this forward method, and this forward method is going to receive the input. And as this figure here, as you see, first we're going to receive this input, and we're going to forward it through our first layer, FC1 will apply to the input. Then we're going to obtain this output, and then this is going to go through the second layer, and then through the third one, and then to the fourth one. Of course, we're using activation functions to take account the non-linearity of the model, as Professor explained. And finally, we're going to return the probabilities after we forward the input throughout our model architecture. One of the most important things here is how we train. We have to define a function. Now that we have our model architecture, we have to define our function, training function. So please pay attention, because this training function is common. The main structure for supervised learning is general. We're going to see the same training function for CNN and RNN and everything. So it's important for you to understand this. First, we're going to define our function, and we're going to tell that our model is going to be training in the PyTorch library. And then for every batch of data, so for every couple of images that we're going to stack together, we are going to first send it to our device, as we did in the example in the Colab notebook. So we're going to send it to GPU, and we're going to zero out previous grads. Remember, this is a loop, so this is recurrent thing. And we're going to initialize our optimizer. So here you can see the code between colors and what is going on. The input goes to the model. The input is going to be forward passed throughout the model, and we're going to obtain an output. We're going to compare this output with the real label. So for example, the image was number 7, and we got a number 6 as the output. So we're going to compare it to the true label, and we're going to compute an error loss with our objective function. So we have a loss, and with this loss, we're going to say, so okay, the weights we had and the biases were not that accurate because we had a wrong label. So what we're going to do, we're going to go back with this loss information, and we're going to adjust the weights and biases according to the error that we had. So by next time when we put the input again throughout the network, we're going to hopefully have correct label. So this is explained here. We compare the loss between our output and the real label. We're going to backward, as you here with this line, only this line, we're doing all the back propagation with all the derivatives and the chain rule computation, everything only with this line. So we don't have to do anything else automatically. And then we're going to call the optimizer step, which Professor is going to explain theoretically in next block. And finally, we can print the results in any format that we want. And this is going to be repeated until we converge to good values. PyTorch library provides you don't have to compute from scratch any of the known laws, for example, MSE, RMSE, cross entropy, the ones that Professor explained. Feel free to explore. There are a lot of loss functions that you can implement. This is really task dependent. So depending on what your objective is, then you have a loss function. You can also implement your own, but I wouldn't recommend implementing from scratch if you want to use cross entropy, because PyTorch already has really efficiently made functions for the loss computation. And for optimizers, which are our tools for updating the weights, how to update the weights, we have, again, PyTorch provides all the known optimizers like stochastic gradient descent, Adam, RMS prop, etc. So you can explore that too. So in practice, what do? We prepare our data and we pre-process it. Usually, as Professor said, this takes time because we have to get rid of noise and everything. And we have to prepare them to be loaded to our whole architecture and model and everything. So after we do this, we are going to set the model architecture. We are going to choose an optimizer and our objective function. We're going to train the model and validate. And until we get a good validation, we're going to iterate over and over with this method. And then that's it. So for practice, we're going to use a very well-known data set that is called MNIST. MNIST dataset consists of 100 written digits like this, and their labels from 0 to 9. The dimension of the images is 28 by 28 pixels, but we're going to flatten them because our first work is going to be with a feed-forward network. So we're not gonna give a two-dimensional input. We're going to give one-dimensional input. And the PyTorch dataset library from Torch Vision provides 60,000 images to train and 10,000 images to test our model. The task is classification, so supervised learning. We'll have classification. The input is going to be an image and the output should be a label between 0 and 9. So now we're going to get started with the practice. Please follow me, and if you have any issue, I will try to go slow, but if you have any issue, please write in the chat. We're going to upload a notebook now. So if you go to the tab file in the provided links that I share through the chat of Zoom, use the HGU MILab link and go to GitHub, this tab. And you have to search and these notebooks will appear. So go ahead and click MNIST Collab example notebook. So now please run the first cell. This should appear. So if you enter to this link, you can access with your email and a password or a code will appear here. So you can copy that and enter your authorization code here and enter. We mounted our drive. So now we can run this to check if the drive was mounted successfully. So here it should appear drive, my drive, and in public, you should have these two files, data and results. I will wait a little bit until you guys can finish this. Let's wait to see if anyone has any issues. Okay, let's move on. First step is we're going to import our libraries and modules. So run this cell. As you can see here, we're importing Torch NN, and some optimizers and functionals and from Torch Vision so we can have the data sets and everything. And now we're going to, next step is to define our model. This is the skeleton of the model. There is no input yet here. So this is the main structure of what we want. We can use different models. For example, this is a CNN, but we're not gonna use this today. We're just going to use a 4-layer feed-forward network for our classification task. So as you can see, we're going to have as an input a 784 image, and we want as an output the probability of each one of the labels from 0 to 1. So go ahead and that cell. So I will not go again through the train function. We define the train function, and here is the forward propagation and back propagation. and we're going to print our results. But let's see in detail the testing. So for testing, we don't want to upgrade our update our weights, because we're just, now that we have the model, we want to see how good it is in unseen data. So we don't have the backward step or the optimizer step. So we just, with this line, with torch no grad, we're telling torch that we don't want to save any information to calculate the gradient or the derivatives. So we're going to load our data as we do. We're sending it to GPU. Then we're going to forward our data through the model, and that's it. We're going to compare between our output and our real target or label, and we're going to compute the loss. Here we are going to transform our probabilities into the label, and we're going to see how many of our predictions were correct with this line. And finally, we're going to print our results as we want, with any format that you like. So let's go ahead and run this cell. Now that we define our main structure, so our model architecture and our training and testing functions, we're going to give the parameters and values. So how many times we want to go through all the data. So this is given by the epochs. The epochs means how many times we want the model to forward all of the data. And we have 2 times here, but you can change this to whatever number you want. Usually the more epochs is better. Batch size is how many images we want to stack together and give to the model at a time. So instead of giving 1 image at a time, we're going to stack 32 images and give them all together for the model to forward pass. These are parameters for our optimizer. So let's go ahead and run. Here we define which device we want. We want CUDA if we have CUDA connected, or else we want just to compute in CPU. We're going to pre-process our images. We can normalize. For example, if the images, the pixels are different values, then this is going to introduce a lot of noise to our data, to our model. The model is going to be confused because we would have images that range really differently. So it could be harmful for learning. So we're going to normalize the data. And there are several more transformations, but we're going to see this more in detail when we study CNNs. And we're going to load our data in batches. As I said, we have to, instead of giving 1 at a time, we're going to stack together 32. This is going to be done automatically by by Torch library. So here in Torch utils, we have this data loader. So we are going to give the data set that we want, MNIST. We want to train it. So we set this true, and we want it to download it if we don't have it, to apply the transforms that we defined, and to stack them in the batch size we defined here, so 32. For the test loader, the loading will be similar, but now we don't want to train. We want the same transformation. So you run this code and you're going to have the MNIST data set loaded. So you can check here, actually, it's going to be loaded in data MNIST automatically. So now let's print, now that we have our loader, let's print an example. We're going to print 1 batch of data, and we're going to check the size, and also to see their corresponding target labels, and we're going to check the size. So if you run this cell, you're going to have something like this. This is a tensor that the size of this tensor is 32, 28, 28. This makes sense. This means we're having 32 images of 28 by 28 pixels, which is correct. This is what we wanted. And we have 32 labels, which is also correct because we have 32 images. So the loader is loaded correctly. So next step is we're going to call our model, and we're going to send it to device. So the model we defined, we're going to call it model, and we're going to send it to the device. We're also going to define which optimizer we want. In this case, we're going to use SGD, and we're going to give the proper parameters. And this is the training loop. So this is how many times we want, remember, the data to be forward through our model to train. And we're going to call both training and testing. So after training finish, we're going to test and so on until we finish the epochs that we chose. After that, we're going to save our model into a results folder that is in the drive. So go ahead and run that. So this is how the iterations that we're going through inside of our training until we finish going through the whole data set, and then we test. As you can see, we have an average already of 91% of accuracy. That means we can classify correctly 91% of our testing data. After 2 epochs, the accuracy increases a little bit more, and we can successfully classify 93% of our testing data. So if you run this, we are going to verify that our model was successfully saved in my drive public results. Okay, I'm going to move on. From the files that we downloaded, the tutorial masters file that we downloaded at the beginning of the class, go to data, and you should have 2 data sets, MNIST test images and PTB. So go ahead and copy the MNIST test images to your drive. You should refresh and check that the MNIST test images are loaded correctly here. Okay, then let me finish this notebook. I'm going to finish real soon. And what I want you to do is to explore the notebook and each one of the parts and see if you have any questions, even if you're not sure how these model architectures and everything are built, or you are not so clear again what every part of the code does, then you can ask me after I'm going to finish, so you can have the whole implementation, and then you can explore by yourselves. So what we did is that we trained for 2 epochs, and we saved our results here. So now we're going to load our model, and we're going to check if our images are correctly loaded into our drive, like this way. So this file should appear. And now what we're going to do is to test. These images over here were not given to the model during training, so the model never seen them. So now what we want to do is, let's go ahead and give one of the images to the model. So what we're going to do is, okay, this is the directory of the image we want the model to classify. We're going to pre-process the image as if it was when we prepare it for training and testing. We're going to call our functions from matplotlib to be able to print the image, and we're going to output our label. So to the model that we loaded, we're going to give this test data that we chose, and we're going to print the prediction. So if you run that, then the model prediction is a 7, which is correct. But as we gave one image, we can give a whole directory. So instead of giving one image file, we can give a file list. The structure is this one. So it's the one that we have in MNIST test images. And now for every image in our folder, we want to do the same thing. So this is exactly the same. But now we can print the testing for several images. As you can see, the model prediction is pretty accurate. So 1, 1, 4, 4, 0.99, and so on. This one that is a little bit confusing, the model still predicts it really well. And we only train twice. So that is pretty good. So we're done going through the whole notebook. Don't panic if you think that this is too much or it's too much to handle the first time. The reason why I went through it like this is now you can explore as much as you want. So feel free to go through the notebook. You can change layers if you want. Be careful with the dimensions of your layers. You can print things inside of this to see what they do in the training function. You can change the number of epochs. You can train more to see if the accuracy increases even more. You can experiment with different batches of images. If I give them more images at a time, will the model perform better or not? So feel free to explore.